Well, there we go. Wish we had Bill Waller here to read his little speech.
I wish this was live. It's not as much fun to interrupt Phil as it is when we're live.
Yeah,
I hope you won't let that stop you.
And jabbing me in the side.
All right, let's thank you everybody for coming. Eve and Michelle just walked in. Hang on a minute. There we go. Thank you for coming and being so indulgent. I'm so far under the weather I could not manage to open up the meeting tonight. We'll have twice as much food next time. Tonight we've got a really cool November presentation, and November is our anniversary month too, and this is 19 years of GAAC.
All right.
Wow.
19 years without all the paraphernalia and trappings, or not a page of Robert's Rules of Order, not a dime in dues. I think it works out pretty well. So
Did you found the club, Michael?
yeah, I did. The first meeting was in the basement of my wife's church, the Lutheran church in Lanesville. And I put an ad in the paper and I got a box of donut holes and a box of coffee, and we're off to the races. It's worked out well. And then we wound up moving in the first year and a half, I think, up to someone's microphone is feeding back on me. So please turn that off. Anyway, that's enough about that. Our speaker is Phil Orbanes. Try Googling this guy. He's got his own Wikipedia page and everything. Very cool
And I'm on
career in the
parole.
gaming industry. Pardon me, Phil?
I said I'm on parole.
You may need to tell Peg, she's new to this, to mute. Margaret Coleman.
In the lower corner of your screen there, Margaret, click on the word that says mute. I can mute her. Hang on. There we go. I'm all powerful here. Okay, anyway, Phil has wandered deeply into the guts of PowerPoint and come out brandishing this magic sword and this PowerPoint full of everything he could hack down. It's an amazing thing, and it has a really cool story to tell. I think a really nice thematic joining of stuff that's coming at us as invaders from space. So very much looking forward to this, and it's got, I've previewed it, and it's got not one, but two music videos and some other sound effects that we know how to make work now. So without further ado, please a round of applause for Phil for volunteering to keep us entertained on a Friday night. Thank you, Phil. It's all yours.
Okay, so share screen, share sound,
And if everybody would mute, please, that would help.
share. Okay, can everybody see the screen now? The starry screen?
Yes, I believe so.
Okay, so hopefully we are going to have a flawless presentation. Michael and I spent some time beforehand to work out a few kinks, and as far as I know, we solved them all. I had a great deal of enjoyment researching and creating this presentation, and I hope you enjoy watching it, because tonight we are going to be investigating invaders from space, in particular, the Aurora and Cosmic Rays. And along the way, we are going to meet all of the scientists, detectives who had exposed their secrets over a long period of time. So the Earth is under constant assault from outer space. We can't do anything about it. Fortunately, it's not harmful, or is it? And that's a major question which will be answered tonight. These invaders come from everywhere. They come from the sun, they come from the Milky Way, and believe it or not, from distant galaxies as well. Now, the Aurora and Cosmic Rays have this in common. They are both triggered by charged particles. They affect molecules in the upper atmosphere, and they are steered by the Earth's magnetosphere. but they also are quite different. Auroras are low energy. Cosmic rays range from medium to massively high energy. The aurora is visible, and primary cosmic rays are invisible. The aurora remains on high, whereas secondary and even some primary cosmic rays penetrate all the way into the surface of the Earth. So unraveling the aurora invasion is the prelude to investigating the far more elusive and complex invader known as cosmic rays. So this is where we start. Now, the first recorded illustration, if you will, of the aurora dates back, if you can believe this, 32,000 years ago in this Cro-Magnon painting. Now, it makes sense because since the aurora is so highly visible, the earliest humanoids would have seen it and pondered it and tried to figure out just what it is. For example, in the year 2600, before the Common Era, Fu Pao wrote, "I see strong lightning moving around the star Su, and the light illuminates the whole area." Now, Fu Pao was the very powerful and influential mother of the then current emperor. And in this particular painting dating from 1570, the aurora is depicted as candles in the sky. Native cultures around the world regard the aurora as the souls of their ancestors returned. This seems to be common, as I mentioned, worldwide. But the aurora continued to baffle even the most learned scientists in successive eras. For example, back in 1590, Tycho thinks northern lights are sulfurous, and he cautioned everybody not to find themselves under the aurora for fear that they would suffer great maladies. 29 years later, Galileo coins the name Aurora Borealis from the name of the Roman god of dawn and the Roman word for the north wind. He thinks it's reflected sunlight from over the horizon. In the next century, Ben Franklin theorized that it was polar moisture and polar electrical charge. And in a sense, Franklin is half right, as we'll see. Of interest, in 1862, the Confederate Army won the Battle of Fredericksburg, and that night, the aurora put on a very powerful display in the skies. The Confederates thought this was a very auspicious sign that they, in fact, would win the Civil War. Of course, they guessed wrong. And I can tell you, I was in Fredericksburg for a convention back in the spring, and they still talk about this particular sighting of the aurora because it's so far south and so rare to see it there. Well, for the next 50 years, scientists spun theory after theory without any success in explaining just what caused the aurora, until this man. And this man is Christian Birkeland, a Norwegian scientist, and he's probably the greatest scientist you've never heard of because of the fact that he was in Oslo and not in continental Europe. When he was a boy, he was fascinated by magnetism and conducted a lot of magnetic tricks and experiments. He was the youngest physicist ever to be acclaimed a professor at the University of Oslo at the age of 30. And he solved the aurora in his laboratory with a device. Now, if you look at the black and white photo on the right, you'll see that he has constructed a vacuum chamber with glass sides so you can see in it. And this large sphere hanging from the top is known as a turella. And this sphere is magnetized so that it actually has a magnetosphere just like the Earth. If you then look on the left, you can see a close-up of a modern recreation. And what he did was to put an electronic filament in the corner to represent the beam of electrons that he felt were coming from the sun, and to create an atmosphere around this solid metal sphere, he coated it with a fluorescent paint. And what happened was the magnetic lines of force directed the electrons from the filament down to both poles and created a glowing oval, which actually duplicated just what he observed when he led expeditions into the Arctic Circle to study the aurora overhead. We may not appreciate it at this latitude, but the aurora actually does occupy an oval. It's not continuously covering the entire pole. And so if we look here, what Birkeland perceived was the existence of a solar wind. As I mentioned, he was outside of the major axis of scientific research in Oslo. The major axis went through London, Paris, and Berlin. It did not detour up to Scandinavia. But he figured out that the particles, the charged particles that were ejected by the sun from solar flares, or as you'll see, coronal mass ejections, were directed around the Earth except at the poles. And that's why the aurora glowed in this oval around both the North and the South poles. A US Navy satellite actually verified his theory 60 years later, despite the fact that during his lifetime, he was considered to be way off target. For example, Lord Kelvin in England could not believe his theory of the solar wind because he was convinced that in the vacuum of space, no particles could travel. So what is the solar wind? It's a plasma of ionized particles ejected from the sun in solar flares and prominences. And here's an excellent picture of what is known as a coronal mass ejection, a CME. And Mario was kind enough to provide this to me. Now, what happens in certain solar flares, like the one in this picture, is the magnetic fields inside of the flare twist and turn. And when they become strong enough to be repulsive, they break loose from the sun, and you get this ejection of a massive amounts of particles. And the particles are either ionized hydrogen, which is basically one proton and a separate electron, or the nucleus of a helium atom, which is known as an alpha particle, plus 2 electrons. And by the way, the electrons are known as beta particles. So this deadly wind was named in the 1950s, and it blasts towards Earth at speeds that can exceed 1 million miles per hour, which means it takes about 4 days for it to get here. And believe it or not, it has a sound. And this sound was recorded by the Parker Solar Probe when it went into the sun, or before it went into the sun back in 2018. And this is what the solar wind sounds like. Could everybody hear that? Okay, so now the aurora, as we all know, comes in a variety of colors, of which probably the most dominant is green. The color that you see in an aurora indicates which gas molecules in the atmosphere are being excited by the ions and electrons that are descending down to the poles. For example, green is oxygen at low altitudes. Purple is highly energized nitrogen. Red is high altitude oxygen. And finally, blue is low altitude nitrogen. Now, believe it or not, the aurora actually has a sound. And my friend Jen Karp in Finland tells me that he's heard it on more than one occasion. And I've got a recording of one such sounds, and it is rather spooky. The spooky part comes at the end, and this might be a little too loud. I'm sorry if it is, but it goes for about 20 seconds before it really gets to the spooky part. All right, so I would be curious to hear that someday, but apparently you have to be in Scandinavia. So the intensity of the solar wind determines how far south the aurora will be visible. And these isobars are a measurement of geomagnetic activity on a scale known as KP. And 3 is usual, and in order for us to be able to see the aurora, we need something a little bit greater than 7. And as you can see, Northern Virginia requires a KP that's quite a bit higher than that. Now, I draw your attention on the upper right to Reykjavik, Iceland.
Hey,
where
Phil,
the-
Phil, can I interrupt for a second? I'm sorry.
Yeah.
Mario's been trying to get your attention for about 45 seconds here. For
Who
something.
has?
Mario.
Oh, Mario.
Yeah, just a quick question. I don't mean to interrupt. If you want them at the end, let me know. But what makes the sound? I don't understand. These are charged particles that are heating the air.
Well, the
So
air is in motion. The charged particles makes the air move, and so you get this oscillating sound. And, you know, as I said, if I didn't have an eyewitness on the ground who has heard this time and again, I wouldn't have believed it myself.
okay,
Yeah.
so basically it's heated air.
Well, it's not so much heated. By energized, you know, the electrons in these particular atoms are moving up a level, and that's creating, well, I guess in a sense it is creating heat, because that's why the air is in motion, especially if it's lower altitude oxygen, because that's relatively close to the ground, and the sound can easily be transmitted from there through, you know, the air between us and the surface. Okay, so anyways, Reykjavik, is that okay, Mario? Okay, so Reykjavik, Iceland, as you'll notice, is above the KP3 line, and that will come into play on a subsequent slide. So, is the aurora dangerous? And the answer is not unto itself, but the coronal mass ejections are dangerous or potentially dangerous. A truly massive CME would reach the Earth in just one day. It would stretch our magnetosphere behind the Earth and cause it to snap back as a massive geomagnetic storm. So literally what would happen here is that a massive CMA would merge. The solar wind would actually merge with our magnetosphere. It would not just be deflected, you know, off into space toward, let's say, Mars. And like a rubber band, it would stretch the magnetosphere to almost a breaking point, at which point it would snap back. And the onrush of charged particles at that point would be potentially grim. Many power grids around the world would fry. It could take 4 to 10 years to repair them, and the cost could be $3 or more trillion US dollars. So this is always something that, you know, we need to be concerned about. Now, to finish the presentation, I have some images because, you know, the aurora being as beautiful and varied as it is, so we can't go out without looking at them. So the daughter of a longtime co-worker spent a year in Reykjavik as a student and working there. And she and her friends would go to this peninsula with the red dot on it, just outside the city, to observe it. And fortunately, they took some photos. So here's the first one. As you can see, this would be low altitude oxygen. And if you if you look carefully, you can see the Big Dipper inside of it. Well, the Big Dipper is going to be more obvious in the next photos. So the other thing that's really nice about Reykjavik is just how dark the skies are. It's something that we would love to have here more often. And here you can see the Big Dipper pretty clearly on the left. So now to close out, we're going to look at a gallery of aurora photos, and we're going to set this to music, hopefully to make it a bit more enjoyable. And if you look carefully in a lot of the pictures that you're about to see, you'll spot familiar constellations, which of course will include the Big Dipper.
When day is done, stars shine, the night has come and lovers' hands entwined. I'm all alone, but I dream of your beckoning kiss, and I know you'll come to me, Aurora Borealis. When you are here, I'm in heaven. I feel your love so deep without a question. My eyes, they fill with rapt attention. And when you're gone, I fade inside. I cry, I feel as dark as a dreary starless sky. You are divine, so right. Your face, it shines like winter's northern lights. Are you for real? Won't you stay in my arms in bliss? But I know you won't, Aurora Borealis. Light of my life, hold me so tight, kiss me goodnight, then you are gone.
Okay, so now that we've covered the preliminary, we come to cosmic rays. Now, prior to the late 19th century, mankind knew exactly this much about cosmic rays. But as all good scientists do become detectives when a cosmic mystery is afoot. And here's an example, Columbo Stein. They got to work on it. Now, the first thing that triggered awareness of cosmic rays was an invention. It was actually more of a curiosity than a serious device, and it was called the electroscope. And here's, in particular, the one that made the difference. Come on. Oh, is the gold leaf electroscope. And here's how it worked. So 2 gold leaves were suspended on a rod in the center of a glass chamber. A rubber insulator separated the rod from the glass. Whenever a charged object touched the rod, the 2 leaves at the bottom sprung outward like wings. Now, of course, the reason for that is they both had the identical charge, positive or negative, and so that's why they were suspended in space. However, inevitably, the two leaves began to collapse and then simply would go back to their original dangling position. And no one could figure out why this was happening. And this was true no matter how perfectly the electroscope was built. The leaves lost their charge and they grew limp. And no explanation could be found for this. It happened day or night, hot or cold, in the depths of mine or on top of tall structures or hills. For a century, there was virtually no progress in trying to figure out the cause of this. And as this snail points out here, scientists didn't even know where to go. So that's one reason why progress was slow. Then came 4 breakthroughs very rapidly at the end of the 19th century. William Röntgen discovered X-rays in 1995. Henry Becquerel discovered natural radioactivity in 96. J.J. Thomson discovered cathode rays, which are electrons, the following year. And finally, in 1898, Mr. and Mrs. Radioactivity, Pierre and Marie Curie discovered the first 2 radioactive elements, radium and polonium. And I want to take a moment here just to point out that Christian Birkeland, who we met earlier under the Aurora section, actually discovered X-rays a month before Röntgen, but he was not able to get attention to that fact. And he provided J.J. Thomson with all of the research necessary for Thomson to build a device and claim discovery for cathode rays. Thomson conveniently did not give Birkeland any credit at the time, and only got around to doing so in about 20 years later, after Birkeland had died tragically. Now, Birkeland not only was instrumental in these 2 discoveries, but he also predicted and demonstrated how atomic nuclei could be shattered and create enormous amount of energy. He perfected a magnetic railgun, and he even worked on rocket propulsion in Norway that preceded by decades research done in America, for example. Birkeland died from what either was an accidental or intentional overdose of a sleeping medication while he was in Tokyo during World War I. So that's one reason that he is so little known. He just, disappeared from the scene before he was 50 years of age. Anyway, the importance of these 4 discoveries is that they demonstrated that the atom is not sacrosanct. And up until this point, the accepted theory of the atom was known as the marble. And it was conceived by this man in 1808, John Dalton. And after studying chemical reaction and mass ratios, he had 4 conclusions. 3 of them are pretty accurate. Matter is composed of extremely small particles. 0.3 atoms of a given element are identical in size, mass, and properties, and atoms of a specific element are different from those of another element. But his point number 2, that atoms are indivisible and indestructible, was shattered, by the foregoing experiments. This was now, so the marble theory was now replaced by the so-called plum pudding theory. And in the plum pudding theory, atoms were a positively charged sphere inside of which were negatively charged electrons. And there was a different number of electrons for each, according to each element. The proton had not yet been discovered. The neutron was way in the future. And this was the best that scientists could do, having finally discovered one of the particles making up an atom. But the discovery of the electron and radioactivity turned attention back to the electroscope dilemma. Röntgen proved that X-rays could discharge an electroscope. Radioactive elements exposed to an electroscope did discharge it, but the electroscope continued to discharge when not exposed to either of these. And so the mystery continued, just why? And it took this Scottish scientist, Charles Wilson, to deduce the main source of this discharge. And for him, this was, or I should say, in the scientific community, this was a terrific leap of faith. He determined, or he surmised, that the production of ions could be explained as due to sources outside our atmosphere of enormous penetrating power. So this leap of faith was once again profound and controversial, and it seemed to lack a means to prove it until Mr. Balloon, and that was his nickname, astrophysicist Victor Hess of Austria, and he became the father of what became later known as cosmic rays. Now, what Hess figured out is that if in fact the source of the ions were coming from space, the higher you could get off the surface of the Earth, the faster an electroscope would discharge. And so he and a pilot and a weatherman took to the air 16 times in balloons filled with coal gas. The problem with coal gas is they could only get up to 5,000 feet and the results were inconclusive. So on Flight 17 on 7 August 1912, Hess and his crew got into a balloon filled with hydrogen, which of course unto itself is highly dangerous. And they reached 16,000 feet and discovered that the electroscopes that he had brought with him discharged 400% faster than on the surface. And I should point out, as most of you know, when you get to 10,000 feet, the brain starts to become starved for oxygen. So at 16,000 feet, you're feeling pretty groggy. But he concluded and verified, if you will, the theory that a radiation of high penetration power was entering the atmosphere from above. And other scientists conducted subsequent flights with unmanned balloons that reached as high as 50,000 feet, and they all confirmed Hess's theory. Now, at about the same time, this man, Ernest Rutherford, discovered the proton. And by so doing, he created a new model of the atom, and we said goodbye to the plum pudding model. In his model, there was a nucleus, which consisted of one or more protons surrounded by a swarm of electrons, depending on the element. Rutherford, who was a New Zealander, also discovered the concept of the radioactive half-life, and he differentiated and named the alpha and beta radiation that we saw earlier. The alpha radiation being the strip nucleus of helium atoms, and beta radiation being charged electrons. And as a result, Rutherford is known as the father of nuclear physics. And two new inventions helped in the search for cosmic rays. The first was the cloud chamber. We'll talk more about that in a moment. This revealed the track of cosmic ray particles. And the second was the Geiger-Müller counter. Now, we all know this counter today simply as the Geiger counter, but the original device invented by Hans Geiger was finicky and not sensitive enough. But when he revised it with the help of his grad student, Müller, the so-called GM counter became very sensitive and enabled cosmic rays to be detected and noted by a click, which of course we know to be very familiar today. Whoops, I skipped past that. But anyways, there was the tick sound of the Geiger counter. So just what is it that's striking the Earth? Does it come from outer space or from our own atmosphere? And the answer arrived in 1929, and it was both. Primarily from outer space, but secondarily from smashed atoms in our own atmosphere. And these two Germans were responsible, Walter Bertha and Werner Cohausen. And they determined, or I should say they verified what Hess had figured out earlier. And They worked with Hans Geiger and they perfected a technique, which is, I'm going to show it to you in a moment, that exposed the truth. Namely, that primary cosmic rays strike atoms in our atmosphere, or molecules in our atmosphere, and create secondary cosmic rays. So let's look at their experiment. It's really quite ingenious. They built a large lead box and they lined it with iron. That was the first two parts of this device. Now, one reason they did this is because they wanted to block natural radioactivity coming from the Earth, which this very successfully did. Then they suspended in the center a gold bar because they knew gold was much more dense than either iron or lead. Of course, they had to borrow this, probably, I think, from a bank and put up a security deposit. And on top of and below the gold bar, they mounted a GM counter. And their figuring is that a small portion of cosmic rays would have enough energy to reach the surface of the Earth. So if you look on the left, the green line, the green vertical line is named CR number 1. That's cosmic ray number 1. What they thought would happen would be that the majority of cosmic rays penetrating would actually make it through the iron. They would trigger the GM counter above the gold bar, and then they would get absorbed into the gold so that the counter below would not tick thereafter. They thought a small portion of them, as noted on the right as CR number 2, would be powerful enough to go through the lead, the iron, the gold, and strike the counter below, and therefore give you a double click. But what they found was that 75% of all the incoming particles possessed enough energy to trigger both counters. And this was far greater than the 5% that they thought. This strongly suggested that primary cosmic rays were frightfully energetic, that some could reach the ground and others triggered massive showers of secondary charged particles. So if you look on the upper left, here comes a primary cosmic ray from outer space. A collision occurs. And when that happens, it creates a chain reaction, a cascade of particles are either set free or created in our atmosphere. And the initial energy from the primary is so great that perhaps as many as 1 billion secondary particles are triggered from it. So this man, Robert Milligan, is the man who names this phenomena. And Milligan was a very, well, he names them, I believe the radiation is high energy gamma rays, and I proclaim them to be cosmic rays. And this misnomer stuck. So for a variety of reasons, Milligan did not think these were particles. He thought that they were high energy gamma rays. Now, in the electromagnetic spectrum, the highest energy photons are gamma rays, and it's all that we knew in that era of the 1920s and 30s that seemed to have the energy necessary, in Milligan's eyes at least, to be called cosmic rays. He was at Caltech. He happened to be a fairly stubborn experimental physicist. And the reason why he was so convinced about cosmic rays being photons is that he thought that new atoms were constantly being created in outer space through the collision of hydrogen atoms to create heavier and heavier elements, and that gamma rays were, as he put it, the birth cry of these new atoms. He personally disliked the KB experiment because obviously that was conclusively proving that it was particles and not rays. And he would take on any comer who disputed him, especially this man, Arthur Compton. And Compton was a noted physicist and a cosmic ray globetrotter. He is the man who created the Compton effect that demonstrated that light is both a particle and a wave. And then he turned his attention to cosmic rays. He led expeditions around the globe and in the process proved that cosmic rays were more intense at the poles than at the equator. And that's a geomagnetic similarity to the aurora. And it was very supportive of the idea that cosmic rays were charged particles, or as scientists were increasingly calling them, cosmic bullets. So Milligan and Compton duked it out in the 1930s in a famous debate. And obviously, Compton was arguing that they were particles, and Milligan was, arguing for rays, but Compton won. The evidence was just overwhelming, and Milligan eventually came around. And one reason he came around is because by this point, his name, Cosmic Rays, had stuck, and no one was attempting to usurp the name and replace it with something with the word particles in it. So his name is with us to this day, even though it's incorrect. Now, Albert Einstein also demonstrated a Geiger-Müller counter at the 1939 World's Fair. So no, he's not being frisky in this picture. That's actually his daughter sitting in his lap at the fair. And I'd point out before I go on here that Einstein really didn't want to do this. He regarded the demonstration at the fair as being kind of beneath his dignitary, but he was persuaded that it would be very good for science if he lended himself to the demonstration at the fair of Geiger-Müller counters that were going to count cosmic rays that actually came into the pavilion where the demonstration was taking place. But unfortunately, when the 10th cosmic ray was captured, the main light show overloaded and it caused a blackout. And Einstein was heavily embarrassed by this. So cosmic rays were actually the first particle accelerators. And in 1929, Carl Anderson at Caltech built a giant cloud chamber to study the energies of electrons present in his cosmic radiation. And you can see it here in this picture. You'll note that it's encased in coils of wire. That's because he needed to create a electromagnetic field around the cloud chamber. And so much electricity was required for this that the power source for his device was the main generator for the entire university. But he was almost instantly rewarded because in this cloud chamber photo, to his surprise, he not only observed electrons from cosmic rays, but he saw the trails of positive electrons, which were quickly named positrons, and they were the first antimatter particles ever observed. And if you look at the Y-shaped figure in this picture, the particle curling off to the right is a normal electron. The one disappearing on the left is a positron. And this launched a whole new field, that of particle physics, which is both weird and complicated. Now, tracks inside a cloud chamber. What happens is that inside the chamber, supersaturated vapor condenses in the tiny liquid droplets around the path of penetrating ions and charged particles due to their charge, and the shape of the path determines the particle. So for example, in this particular photo, the circular tracks are electrons, but this one, the straight line, that's a cosmic ray. Now, cosmic rays initially were thought to be normally known particles, neutrons, electrons, protons. And the neutron, I guess I'm not sure if we've come to that yet, but the neutron is discovered in 1932. 2 years later, Anderson and Seth Nettermeyer observed the first cosmic ray specific particle, which we know today is the muon. And here's the track of the muon. Now, it's negatively charged, but the reason it's called a fat electron is because even though it has the same charge as an electron, it weighs 200 times as much. Initially, it was thought to be a particle very similar to a proton, but as it turns out, it's actually in the same family of particles as the neutrino and the electron, which are known as leptons. And most significantly, and you'll see where this comes into importance in a bit, it only lives for 2.2 millionths of a second. And the discovery of the muon opened up the likelihood of many more exotic particles never dreamed of before. For example, the neutron itself, we'll get to that, but the neutron is discovered finally in 1932. And that leads to a theory of the atom, which is very similar to the modern theory. And in this theory, the neutrons and the protons bond in the center of the nucleus, and they are surrounded by orbiting electrons. And in this particular case, I'm showing a lithium atom, which has 3 protons and 3 electrons. And lithium is going to also be highlighted on a subsequent slide. So we'll get back to lithium a little bit later. So the particle zoo now begins to be stocked. And the next particle to be discovered is called the pion. And as it turns out, the pion gives birth to the muon. So the muon is not directly caused by cosmic ray collisions. It's the result of another particle being born in a cosmic ray collisions. And in this particular picture, you can see the pion on the right is born through a collision. It very rapidly decays into some neutrinos and the muon. And the muon in time comes to rest and decays into an ordinary electron and a pair of neutrinos. And this, by the way, was actually taken through nuclear emission plates. There's another particle that was discovered soon thereafter is called the kaon. And both the pion and the kaon are mesons. And it's not that I want to get too deeply into particle physics, but particles that have mass are composed of quarks, the most common of which are the neutron and the proton, each of which has 3 quarks. Well, mesons, which comes from the Greek word for middle or intermediate, have 2 quarks. And so that's just the explanation of what mesons are. Now, the reason why I do mention this is because at first, the muon was called the mu meson, and that's because it had been predicted brilliantly by a Japanese scientist named Kawaka. And it was thought that the muon was his long-awaited meson, which he felt was necessary to bond protons and neutrons together, but it was a mistake. Actually, it was the pion and the kaon that were more toward what his theory predicted. Now, 10,000 muons penetrate your body every minute, and yet their short lifespan suggests that only a few should ever make it from 10 kilometers on high to the ground. So the reason why 10 kilometers is important is because muons come into existence somewhere between 30 kilometers and 10 kilometers above the surface of the Earth. So even if you take the lowest altitude where they can be born, and you reckon that they're traveling at 98% of the speed of light, and their lifespan is known to be 2.2 millionths of a second, there's no way that they can reach the ground, let alone penetrate your body, but they do. So what's going on? Well, it's simple. The muons don't care about our reference frame here on Earth. They're traveling at nearly the speed of light, and as a result, time is slower from our perspective if you're a muon, and they think that their life is 200 millionths of a second. Now, that's more than enough time to penetrate through you and reach the Earth. And what's wonderful about this reality is that this is a very elegant proof of Einstein's theory of special relativity. And that's why, he feels this is special. It really is. It's really a nice, additional proof to the spectacular theory by Einstein. So now we get to cosmic rays and energy. And here the question is, what exactly is an electron volt? And that's very important to measure the intensity of any photon or particle that we're going to be talking about. So cosmic energy, cosmic ray energy is measured in electron volts, and here's the definition of what it is. Now, solar winds, the energy in a solar wind is somewhere in the neighborhood of a couple of thousand electron volts per nucleon. A large eruption from the sun that produces a CME can produce particles with energies in the range of 10 million electron volts. Primary cosmic rays that have a minimum energy of 450 million electron volts can reach the ground. And as we'll see on the next slide, some are far more powerful. So here's some common voltages. In the days of cathode ray displays for our TVs, the electron gun was shooting electrons, each of which had 20,000 electron volts. Earlier this week, I had to go to the dentist for a checkup, and they gave me x-rays, and so I was subjected to 200,000 electron volts. Typical energies from nuclear decay are in the order of a few million electron volts, but cosmic rays range in energy from 1 million electron volts to 1,000 trillion electron volts, and some of them are even more energetic. And it's just worth noting that we have never been able to create or to generate particles with more than a few million electron volts. So cosmic rays are far more powerful. And some of them are quite extraordinary. So by the 1940s, we had a pretty good idea of what primary cosmic rays are. They consisted of protons, helium nuclei, electrons, positrons, and antiprotons, and other atomic nuclei up to iron. Protons and alpha particles, which are the first two on this list, represent 99% of the total. Secondary cosmic rays produced in our atmosphere from collisions consist of protons, neutrons. Of course, that makes sense because atoms are being broken apart. Positive and negative pions, positive and negative kaons, muons and neutrinos, and also from electrons. Now, the question that we posed up front is, are they dangerous? And the answer is, cosmic rays typically do not damage humans except astronauts in space, which is a serious concern. And also they could cause bit flips in computers. So every now and then a computer malfunctions because the cosmic ray hits a bullseye. Astronauts on the moon reported seeing blue flashes with their eyes closed. That's because cosmic rays were actually penetrating their eyeballs. And there is as yet no practical shield against cosmic rays in space. Now, this is really significant because astronauts who are going to spend months going to Mars are going to be subjected to a lot of cosmic rays on the voyage there, unless some type of a shielding can be developed to protect them. And by the way, the really bad thing about excessive exposure to primary cosmic rays is that it increases the likelihood of cancer. So a cosmic ray shower has this type of if you will, a tree of particles. Protons from 30 kilometers or above are set free by a primary cosmic rays, and that in turn leads to pions, which in turn leads to neutrinos, which are the orange lines, and the light blue lines are muons. And as you can see, commercial pilots flying at a normal cruising altitude do receive a lot of exposure to cosmic rays as well. And over a long career, they might have a slightly elevated chance of cancer as a result. And you can also see that some high altitude balloons can almost reach the altitude where the primary cosmic rays start their collisions. Secondary cosmic rays are I put this up without, I'm not going to explain everything here, but you can just see how if an air molecule is hit, you can see what's created and approximately where as a result of this cascade of particles that ensues. Now, one of the interesting things about cosmic rays is that they have just about the same relative presence of elements as the abundance of the elements in the universe, with 3 exceptions. And the exceptions, as you can see here by the dip on the left, are lithium, beryllium, and boron. Cosmic rays produce, or there are more of these atoms in cosmic rays than there are in the universe. And there is reason why these 3 elements in particular are not more prevalent. But why is this so? Well, the answer is because secondary collisions create these rare ions in our atmosphere, primarily from collisions with carbon dioxide or with nitrogen. So the final big question that remains to be answered is, where do they come from? Now, from the launch of the very first satellite, primary cosmic rays were detected and analyzed above the Earth's atmosphere. Now, this was a real breakthrough because up until this point, about the best we can do was high altitude balloons. But here's a picture of Explorer 1, which was launched in the early days of 1958. And included in the limited instrumentation in this satellite was a cosmic ray detector. That was also true for the Pioneer family and for Mariner 2, which went to Venus in 1962. And it was Mariner 2, by the way, that verified Birkeland's theory of the solar wind. These satellites are also notable. The Voyagers have cosmic ray detectors, and the Lunar Recon Orbiter and the Fermi Gamma Ray Telescope have very sophisticated cosmic ray detectors, which provide a lot more information than the earlier satellites. So armed with devices above the atmosphere, we now have a much better understanding of primary cosmic rays. We also have these balloons. These balloons were launched over a course of 15 years from the Antarctic. They were given the name CREAM, which stands for Cosmic Rays Energetics and Mass Experiment. And you may remember that Jim Nordhausen, who was here this summer, gave us a nice insight into the ones that were flown out of McMurdo. So that we now know the origin of cosmic rays, thanks to all of these devices. 1 is the sun. 2, supernova. 3, blazars. Neutron star collisions and other violent events also produce galactic cosmic rays, but they are rare because the phenomenon itself is rare. So let's talk about the sun. Well, the CME events and solar flares produce cosmic rays with a relative, let me see, can I get this? Yeah. There we go. With energy somewhere between 10 million and 10 billion electron volts, and the shock accelerator of magnetic fields linking and folding back on themselves provides enough repulsive energy for ionized hydrogen, helium, and traces of heavier elements to escape the sun's gravity and pierce our atmosphere and create secondary cosmic rays. Oh, I got to go back to here. Second is supernova. Now, in the Milky Way, supernovas are the primary source or the prime source of cosmic rays. Stars far more massive than the sun explode about 1 every 50 years. Shock waves initiated by supernova accelerate particles to nearly the speed of light, and these cosmic rays possess trillions of electron volts, sometimes more. The Crab Nebula, by the way, is shown here. Finally, blazars. Now, blazars are a type of galaxy powered by an enormous black hole. galaxies that have a active nuclei are typically known to us as quasars. There's a few other related types, but a blazar by definition is a quasar or related galaxy whose relativistic jet is pointing directly at the Earth. If it's not pointing at the Earth, it's not a blazar. The massive black holes at the center of quasars in particular are ejecting particles from both the north and south pole. So if either pole is pointing at the Earth, that's a blazar. And it's like staring down the barrel of a black hole because it's firing cosmic bullets at us with energies of up to 10 to the 15th power of electron volts, sometimes even more. A blazar radiates enough energy, radiates energy across the entire electromagnetic spectrum from radio waves to gamma rays, in addition to countless particles. And those countless particles become cosmic rays. Now, here's a fly in the ointment. In 1949, Enrico Fermi explained that how cosmic rays achieve such phenomenal levels of energy and speed. It's because as they travel from their source, whether it's from a supernova or from a distant blazar, or even which is another galaxy, the particles enter molecular clouds of charged hydrogen. And when this happens, they get whipped around and accelerated. And this happens time and time again until finally they're moving at nearly the speed of light. Now, there's a downside to this, and that is that the process causes cosmic rays to forget their origin. Fermi acceleration, as it's known, causes the messenger, the cosmic ray, to lose its message. And the reason is, as you can see in the source on the right, all of these curlicue paths coming out of it ultimately reach an observer on Earth, but by the time they get here, they're coming in a direction that bears no relationship to the location of the source. And that's frustrating because it means, with rare exceptions, and I'll be pointing this out in a moment, when they get to the Earth's atmosphere, we just can't trace back and figure out precisely where each one came from. Even particles from the sun sometimes arrive on the opposite side of the Earth. So can we ever hope to pinpoint the exact origin of a cosmic ray? Well, all is not lost. And if we go back to Columbo-Stein, he points out that they can conveniently forget where they came from, but there's one thing they can't hide, and that's their energies. So the energy of a cosmic ray reveals the distance it has traveled. Generally, the higher the energy and speed, the longer the cosmic ray has been bouncing around the universe, which explains why some of them actually get here from galaxies that are tens of millions of light years away. So if we can determine if a cosmic ray came from the sun or from the Milky Way or from a faraway blazar, at least we have some information about its source. And this particular diagram, which is really coming to the conclusion of our analysis of cosmic rays, is the sum of everything that we've learned. It's called the cosmic ray energy spectrum, and I'll just take a moment to explain it. The two axes, the vertical axis is the number of cosmic rays, and it's logarithmic, and the energy in electron volts of each cosmic ray is measured on the horizontal axis, also logarithmic. The yellow line is the relationship between the quantity of cosmic rays that penetrate our atmosphere and their energy level. So as you can see in the upper left, the sun is responsible for the largest amount of primary cosmic rays, but they're all low energy compared to the middle component, which is called the galactic component, and especially the bend in it, which is known as the knee. And that's because if you look at the three colored curves, the cosmic rays caused by these three sources, supernova, other galactic sources or extragalactic sources are summed into the yellow line. And as you get down to the bottom where the ankle and the foot point to the lower right, almost all of those cosmic rays of the highest energy, but the fewest number, are coming from extragalactic sources. So this is a very effective tool to visualize how energy equates with source. So there's one notable exception, and that's this particular blazar. This blazar was the source of a super high energy neutrino that slammed into the massive detector in Antarctica nicknamed Ice Cube back in 2017. Observatories worldwide searched for and found the source of this neutrino. And this was possible because the neutrino, as the name implies, has no electrical charge. And that means that it's not subject to Fermi acceleration. It traveled in a straight line from its source, and we were able to determine that it came from a blazar in the constellation Ursa Major. So at least we have a bead as to its location. And now we have the oh my God particle. This particle was detected in 1991 in Utah. It had a massive energy of 3.2 times 10 to the 19th electron volts. This ultra high energy has never been matched and seems to defy the laws of physics. Another good thing about this is that it was impervious to Fermi acceleration because of its great initial speed. And once again, it seems to have come from a source in Ursa Major. And I think that's, quite an interesting coincidence. Now, just how energetic is 3.2 times 10 to the 19th electron volts? Well, it equals the energy in a rock slung by David at Goliath, and yet that energy is contained in one tiny invisible particle. So that gives you an idea of just how powerful this was. So future challenges, where do we go from here? Well, it's interesting to note that most of the carbon-14 that we use to date organic materials is created by cosmic rays and atmospheric collisions. And that supply is steadily decreasing. And why is this? It's because the supply got to be very substantial during the nuclear testing era. And when the test ban went into effect, we no longer were creating carbon-14 here on Earth, thank God. But the supply is becoming, more precious, and we need to create a way of readily making carbon-14. And we must ensure that cosmic rays are not continuing to alter chromosomes and DNA, which I'm coming to. And we have to find a way to protect astronauts from cosmic rays on long space flights so they don't develop increased risk of cancer. And we also need to verify if cosmic rays are affecting weather and climate change. And there's a number of scientists who are not so much convinced by this, but very curious and really want to know for sure. And then last, we need to determine if cosmic rays affect genetic handedness or chirality, which in Greek means hand. And we're going to talk about that now. Now, chirality is a major topic unto itself, so I'm just going to lightly touch it. But eons ago, daughter electrons from muons likely cause right-handed biomolecules to vastly outnumber their left-handed counterparts. And the reason for this is that the electron inherited the magnetic spin from their mother muons. And that spin is in one direction only. And as it so happens, these electrons are more attracted to right-handed DNA than left-handed DNA. Now, what do I mean by that? Well, in the classic example of handedness is that while your left hand is the mirror image of your right hand, there's no way you can twist or turn your left hand to exactly match or that is to go behind or in front of your right hand. You can only do a mirror image. And that's the topic of chirality. And opposite-handed molecules cannot be superimposed. So if you look at these two molecules, you may think that they're identical. But if you turn or twist the one on the left and say place it 180 degrees behind the one on the right, it's not identical because the R component will be pointing backwards, not forward. And that's the difference in handedness. So what's the significance of the fact that DNA is today entirely right-handed? Well, if we create a left-handed version, it's immediately expelled from the DNA and breaks it apart. So how did this happen? Because when scientists look back at the earliest forms of primitive life, they see evidence that handedness was even-handedness back then. Of course, if the daughter electrons from muons are affecting the right-handed ones, they're causing the right-handed DNA back then to mutate at a faster rate, which means it becomes superior. Now, another reason why this is profound is that theoretically, muons are universal. Everywhere in the universe, muons are striking planets where they come into being in secondary collisions. And that means that if there is something like DNA, or there is DNA on other planets, they would all be mutated to be right-handed, just as on Earth. So we don't have the means yet to absolutely prove that, of course, but that would be very profound because it would say that there would be something common to biological life throughout the universe, thanks to cosmic rays. So can we use cosmic rays? Well, it turns out we can, because we have this endless supply of muons that's available everywhere, 24 hours a day. We can use them to see inside of structures that are too dense or thick for X-rays to penetrate. This has already been done in one of the great pyramids, or one of the pyramids, and a chamber never before discovered has been found. And of course, the way this is done is the muons are penetrating from above, and you simply need to make a record of those that are coming in. And then if you have a means underneath, you can see which ones are coming through, and you actually end up with the equivalent of a much better X-ray. Muons can also be used to scan cargo ship containers to detect illicit nuclear materials. And a muon metric positioning system can be devised for precise undersea positioning. Now, this is really important when you're trying to locate, let's say, the foundations for an oil rig offshore. And then one more thing is cosmic ray neutrons in the soil can be measured to determine moisture content in dry locales. So one of the key things to do in a dry area is to water vegetation when it needs it, but not excessively, because water is precious and expensive in these locales. And since cosmic rays create neutrons, the neutrons in the soil are going to be abnormally large due to cosmic rays, and they can be used as a measurement for this moisture content requirement. So now we come to the end. And before we close, we're going to look back and have a review of everything that we've learned about cosmic rays in 60 seconds, accompanied by a symphony. Here we go. Okay, thank you very much.
Wow, a thoroughly entertaining presentation.
Thank you, Phil.
Thank you, guys.
All you gotta do is give Fermi back to seeing his name and it'll be perfect. That was great.
All right, are there any questions for Phil?
How long did it take you to make that?
I think 6 weeks, but that's because I had to learn the techniques in PowerPoint as I
Of
went.
course.
Yeah. So as I knew I needed something, I had to figure out how to do it. By the
That
way,
was
of course, like
that was
everything
great.
else, once you know it, it goes very fast.
Do you make more?
I can easily make more now. Anybody can make more if they know the techniques.
Wow.
Phil pretty much owns November, the way Kelly Beatty owns December, so he'll be back.
It's our
Oh yeah,
Thanksgiving gift.
I'm looking forward to the next one, whatever it might be.
I had a question earlier. You mentioned the Battle of Fredericksburg. 3 years before that was the Carrington event. Wasn't that also a huge producer of
CME?
low altitude visible?
Sorry, what event was that, Fritz?
The Carrington event. That was
Carrington event,
a
yeah.
CME that actually did hit the Earth.
Oh, yeah. The Carrington event was a big event. Yeah.
Zapped telegraph operators because of the current induced.
Right. That was probably the most significant CME, I think, in modern times.
Yeah.
Yeah, fortunately, it wasn't in the modern era when the whole world was run by computers.
Yeah, at this point, that would wasn't there. There was actually a I think in Quebec there was a power outage that was attributed to byproducts of the CME.
Thought that shut down the Eastern Seaboard.
Yeah.
Yeah,
That's
because
a
so
real
much power
warning.
comes from Quebec.
Yeah.
My mother blamed it on me. Like, what'd you do? Nothing.
All right,
Excellent,
with
though.
that vast amount of information, I'm not sure that people aren't just stunned, trying to think of anything they don't know, Phil.
Well, that's nice of you to say, but you know, the corollaries of this investigation are so deep, like, you know, the creation of particle physics, the lack of real understanding of to pinpoint where they come from, and just the process that these scientists went through for a century to determine that this phenomena is not from the atmosphere itself, and that the energy level of some of these particles coming in is beyond any rational guess, you know, like the oh my God particle.
I think what's particularly elegant of all of the sort of images of areas of physics, when you describe the time dilation of these relativistically fast muons,
Right.
that on their clock only live 2 microseconds, right? And they last 200 microseconds in our frame of reference,
Right.
and they get to the surface.
Yeah,
That's-
because two microseconds, you know, because of time dilation, their clocks run that much slower.
Right.
Yeah, it's wonderful. I mean, it's just a
Totally
wonderful
elegant.
proof of this
It's
theory.
amazing.
And Carl Sagan's "We're All Made of Star Stuff" gets a whole new spin from muons, doesn't it?
Well, at least things as
Tongue-in-cheek.
up to the molecular weight of iron, right? I don't know. Do they know why nothing heavier than iron gets through?
Oh, you mean why? Well, the answer is that all of the elements higher than iron do get through, but they're just not measurable on that scale.
Yeah.
And of course, iron is when, you know, a star goes supernova, when it gets to a point that it's trying to fuse iron. And so there's a lot of iron. In fact, I read recently that in a typical supernova, enough iron is created to equal 8 times the volume of the Earth
Wow.
of solid iron, and 20 times the volume of the Earth in oxygen. So one supernova is really a terrific breeder of many elements. Only I think the very heaviest elements require the collision of neutron stars to be created. Yeah.
So that's how we get.
But by the way, something else
on the planet, right?
something else that I learned along the way, and I didn't look into it very deeply, but I did mention that, of course, neutrons and protons are each composed of 3 quarks, and mesons are composed of 2. But really, it's neutrons and protons are composed of 3 valence quarks. Because as it turns out, and this is another thing that's so weird about particle physics, you can have 50 or 100 quarks inside a proton as long as they're all canceled out except for 3. So you can have these pairs sitting in there just coming and going, which makes it seem improbable, when you think about it. But as long as you have 3 valence, you have a proton or a neutron. 2 is a meson.
Bill, reminds me when I was in college, BC had a cloud chamber, and I used to, I recall finally just sitting in front of it, just watching the patterns.
Wow.
It's endless. It's an
Wow.
endless source of entertainment because
Yes.
they never stop. There's always 1 or 2 every second, and it gives you a sense of just, and that's just, something about half the size of a table. If you turn that around the entire Earth, you realize how many cosmic rays are hitting us. But it's they're all around, and they're constant, and they're nonstop. And the patterns they made were just unbelievable.
I would have loved to have seen that. Glad you did. Yeah, to me, it seems so profound that we get penetrated by 10,000 of these every minute. It's a good thing that they don't have a noticeable effect on genetic mutation, like apparently they did, millions of years ago when we were getting started.
Or they continue to, just on geological scales.
Yeah.
Who knows?
By the way, another thing that I think I read is that one way to shield cosmic rays in spaceships is to surround the living area with the water supply that's being carried.
Yeah.
Polyethylene bottles, I believe.
Yeah, maybe that will do it.
With the water supply, that's interesting.
Yeah, you actually have the water tank
Yeah.
for for the astronauts surrounding the living chambers to, and I guess that absorbs the primary cosmic rays.
The dual function. You can drink it and it protects you.
Yeah.
Is it the case that most of that,
The hydrogen
right?
in the water.
But most of the what's hitting us 20 times a second or whatever is actually neutrinos, so that it's stuff that's just passing through us and not really having much.
I think that neutrinos are not even included in that total. I think
That's a different level.
I think you get like millions of neutrinos are constantly
Billions.
a cubic centimeter or square centimeter, but no, it consists of primarily muons, but you also get protons and neutrons and electrons. And one thing I didn't mention is that mesons, which are the pions and the kaons, they absolutely abhor existence. They just don't like to be alive, unlike protons and neutrons, which theoretically live forever. But pions and kaons they just want to decay as soon as possible. So in their frame of reference, the 2.2 millionth of a second life of a muon is ancient.
Yeah.
It's way too much for them.
Yeah, that's considered stable.
Yeah, stable, right?
Well, even a neutron, I've heard that if manage to isolate a neutron outside of an atomic nucleus, it decays after, I don't know what, it's something like 17 minutes,
Really?
which is way longer even than any of these guys by,
Yeah, but still, that's pretty scary.
but it's still not stable on its own as
No.
opposed to protons. Hydrogen ion is just a proton, right? That's
Right.
stable.
Well, they say the middle of the road is a very dangerous place to be. So there you go.
I remember seeing the auroras for hours going to Asia over the polar routes. It was spectacular to just look out the window and there you are seeing colors and what looks like drapes and incredible, absolutely
Wow.
hours
Yeah.
of viewing and the Mother Nature's light show.
Yeah, and it's also varied. It's, you know, that you never see the same show twice.
No.
Well, I grew up in South Jersey, which is, you know, you need a high KP to see the aurora, but twice before I was 10 years old, my mother heard that there would be an aurora show, and I remember her taking me outside, and I also recall it was warm, so I didn't need a coat. And it was just absolutely mesmerizing, those drapes, as you pointed out, the curtains undulating in the sky. That was my first exposure to them.
I worked for a company that made ion beams. I used to watch the vacuum chamber and see the ion beam hitting graphite and the purple of the beam and the white glow of the graphite that the energy was being absorbed by. And we're being bombarded by this stuff all the time without even being aware of it. It's a good thing it's not altering too much of our DNA at once.
Yeah, well, that's for sure.
But, you know, it's an interesting question though about, you know, the rate of mutations and so on, whether, how much do we know about the behavior of the geomagnetic field over geologic time? What was it like around the time of the Cambrian explosion, for example, you know, where we had this sudden, you know, tumult of mutation producing new species, right?
Yeah, well, certainly, you know, the direction of the geomagnetic field is constantly, you know, wobbling, if you will. But the muon, which is created from, you know, a collision with a, or from a pion,
Right.
is basically, it earns its nickname. It's a fat electron, and it has a negative, it has a negative polarity, and it has a particular spin, and that theoretically has been the same forever.
The handedness of DNA is what
Yeah.
you're, right? Yeah.
The chirality of it all. This
Yeah.
is wonderful.
I think,
On a
What's
rainy night.
amazing is how many scientific disciplines intersect to
yeah,
produce.
or that were,
You know,
or that were, that came into existence because of cosmic ray research.
Yeah,
And then
yeah.
where they went from there.
yeah. Well, thank you. This has been just a tour de force. This is,
Thank you.
What-
Thank you.
On
very
that
much.
note, folks, I think I'm going to close the doors here.
Yeah.
Might have
Get
to.
some rest,
I hope
Michael,
you
and
feel-
get
it's a
well.
rest.
Yeah, I hope you feel better, Mike.
Thank
Yeah.
you.
Same here, Mike. Hope you feel
Enjoy
You
better.
can't
yourself.
fulfill all
Tomorrow.
that work. A great product there. Thank you, Phil,
Come
again.
back again, Phil.
Thank you. and
Mike,
thank
let me know
everyone
if you want to
for
make
coming.
that trip
night.
next Saturday.
I will. I'll let you know ASAP. Thank you.
Okay.
All right. Good night,
Bye,
everybody.
everyone.
Right.
Bye, Mike.